Chapter 2, Trigonometry, Lesson 1, Part 2, Calculating arc length and area of a sector in radians. So we're going to have a look at how we can calculate the arc length of a sector. Now, by arc length, of course, I might be referring to, for instance, the arc length here highlighted in red of this sector, which I will label O, A, B for clarity. Now, back in year 10, you learnt how to calculate the area of a sector and also the arc length of a sector. So let's revisit that idea. So arc length of the sector OAB is equal to, and one of the ways in which you would have done this is to perhaps work out the circumference of the whole circle, then divide that by 360 because that gives you the amount of circumference for 1 degree's worth, and then multiply that by theta because that then gives you the amount or the proportion of the circumference that you get for that many degrees. So that's one way of working out the arc length, and that's what we're going to start with. So let's start substituting in information that we know. The circumference of a circle is 2 pi r divided by 360 and then multiplied by theta. Now, of course, the whole point of this formula here is that it is in degrees. But what happens if we work out the arc length in radians? So what I'm going to do is take that formula for arc length and I'm going to make sure that my angles are now in radians rather than in degrees. So I still have 2 pi r, but instead of 360 degrees, what do we know 360 degrees is? We know 360 degrees is the same as 2 pi radians. So in the denominator here, I'm going to replace 360 by 2 pi. And then of course I have to multiply by theta, but what I have to be very clear about is theta must be in radians for this to work. So you can see some very obvious simplification here, hopefully. 2 pi and 2 pi cancel, leaving you with r theta. So arc length of a sector is equal to r theta when we're working in radians. So this formula is a much, much simpler version of the formula that you learnt at GCSE in degrees, but it only works in radians. So make sure you've made a clear note of this. You can work out the arc length of any sector by multiplying the radius by the angle of that sector if the angle is in radians. So back at GCSE, you also learnt a formula, a similar formula for working out the area of the sector, which of course is this area in here. Now let's look back at how you would have calculated this at GCSE. One popular method would be to work out the area of the whole circle. So you've got the area for 360 degrees worth. Divide that by 360, which gives you the area for 1 degree, i.e. the area of a sector with 1 degree's worth of angle, and then multiply by theta, which gives you the area for your sector, for your angle. So we can substitute in pi r squared over 360 multiplied by theta. But again, this particular formula is very specific when we work in degrees. And you can see theta originally measured in degrees, and then 360, of course, is measured in degrees. And again, what we're going to do is now convert this formula to one that works in radians. So again, the pi r squared in the numerator of the formula stays the same, but instead of 360 in the denominator, we have 2 pi, and then we multiply by theta. But again, we must remember theta must be in radians for this formula to work. So what can we do here to simplify? Well, again, we can cancel just a pi this time, which leaves us with a very neat formula, a half r squared theta. So this is the formula which allows us to calculate the area of a sector and it's equal to 1/2 multiplied by the square of the radius multiplied by theta if we are working in radians. So again, make a very clear note of the formula and the fact that we have to be working in radians to use it. So to summarise these formulae, if we have a sector and the angle theta of that sector is measured in radians, then the arc length of that sector is equal to the radius of the sector, which we'll call r, multiplied by the angle theta. So arc length AB is equal to r theta. The area of the sector, again, when the angle is measured in radians, is 1/2 r squared multiplied by theta. And you can see just how much simpler these formulae are than the slightly more complex formulae which are used when we're working in degrees. Now, in a minute, you'll be doing some examples involving using these formula, and some of these examples will require us to use trigonometrical calculations involving angles which are measured in radians rather than degrees. So, for instance, you know that sine 30 is equal to 1/2, but of course that's just measured in degrees. If we're working in radians, we know that 30 degrees is equivalent to pi by 6, so sine pi by 6 must also equal 1/2 in radians. Now, it's going to take a really long time every time you do calculations if you convert your angle to degrees from radians or radians to degrees. So we need to be able to switch very easily into radians mode in our calculator, so our calculator does the work for us and we don't have to do the trigonometrical calculations ourselves. So please watch very carefully, and the video will show you how to set your calculator into radians mode and how to convert between radians and degrees mode on your calculator. So we're just going to take a moment to have a look at how we can use our calculator to perform trigonometric calculations which are in radians. So at the moment my calculator is set in degrees, so if I work out sine 30, you can see I get 1/2 as expected. But we now know what 30 degrees is in radians. It's pi by 6. So what I want to be able to do is put my calculator in radians mode, so when I enter sine pi by 6, I get an answer of 1/2. Now, how do I do this? First of all, press the shift button here, and then press the menu button, but actually really what you're accessing is the setup option, which you can see in gold just above. So when you do that, shift and menu or shift and setup, you get this set of options here, and what we're going to do is just use the arrow key to scroll down until we get to the option which says angle. Now at the moment you can see that it is set in degrees, but what we want is to set it into radians, and you can see these three angle options here: degrees, radians, and then something called rades, which is another angle system that we don't really use. It's quite interesting. The idea of a grade is that there are 100 degrees in a right angle, so 400 degrees in a circle overall, but we don't use that option at all, so don't click on that. What we want to do is to press F2, which takes us to radians, and you can see here the angle is immediately changed to, say, radians or rad. You can then exit from here, and then if you input sine of pi over 6, or pi by 6, which we know is 30 degrees, but in radians, and press your execute button, you will get an angle of 1/2. Now, if you try sine 30, you then get a completely incorrect answer because it's doing sine 30 radians, not sine 30 degrees. So depending on whether you're working in degrees or radians, you need to make sure that your calculator is in the correct mode. Let's try another one. So we know that cos of 90 is equal to 0, but 90 degrees is pi by 2 radians, so let's check that out. Cos of pi by 2 gives us 0 as expected. We know tan of 45 is equal to 1. Well, let's check the equivalent in radians. Well, what's 45 degrees in radians? It is pi by 4 radians. tan pi by 4 we're expecting 1, we get 1. So always important before you do any trigonometric calculation at all, make sure you press Shift, set up, and then always scroll down and check whether your angle is in the correct mode. Now, your calculator has a clear part on the menu at the top here, which tells you which angle you're working in. So at the moment, you can see it's set in radians. If you set back to degrees, it will change to, say, deg there for degrees. Whenever you do a question, make sure you are in the correct angle mode, and you should never be manually changing your angle to degrees or radians yourself. You reset the calculator mode and then allow the calculator to do the trigonometrical calculation for you. It's a much more efficient and quick method of doing this. So we're going to have a look at a very simple example together to see how we can use these formulae. We're going to calculate 4 things about this sector. So have a look at the sector OAB. It's got a radius which is equal to 8 centimetres, and it's got an angle which is clearly in radians because the angle is given as a multiple of pi, so we automatically know it's in radians. I'm not even going to think about what pi by 12 radians is in degrees because I'm going to solidly work out this question using radians. So for part 1, we're going to calculate the arc length AB. So remember, the arc length is equal to r multiplied by theta when we're working in radians. So that's 8 multiplied by pi by 12, which of course simplifies very neatly to 2 pi by 3. Now it's arc length, so it's a length, which means we need to give our answer in centimetres. You may want to then convert that to a decimal value. And please don't be confused, because there is pi in the answer. This is not an angle. We've worked out the arc length by multiplying the radius by the angle, and it's just given us a length which is in terms of pi. And you've done that before. You've worked out the circumference of a circle and given your answer in terms of pi. Please don't get confused at this stage. Not every multiple of pi is necessarily an angle. Lots of things can have multiples of pi in them, but not necessarily be angles. So in this case, we've worked out the arc length. It's 2 pi by 3 centimetres. Now, what about the sector area? So we're going to work out the area of the sector OAB, which, using our new formula, is equal to a half r squared multiplied by theta. So that's a half multiplied by 64, which is 8 squared, multiplied by the angle pi by 12, which gives me an answer of 8 pi by 3 centimetres squared. Remember, it's an area that we have worked out here. So we're now going to use some of these ideas to work out a couple of other things. What if I asked you to work out the perimeter of the sector? Could we do that? Well, the perimeter would be equal to 8 plus the arc length, so 16 plus 2 pi by 3, again all in centimetres. Now, part 4, the last thing that we're going to do is we're going to work out the area of the green segment. You can see it's been shaded in on the diagram. And you've done calculations like this back at GCSE, and we know that the area of the segment is equal to the area of the sector subtract the area of the triangle OAB. And this is where some trigonometry is going to come into play. So the area of the sector is equal to 8 pi over 3. We worked that out in part 2. Now, the area of the triangle. Can you remember the formula for the area of a triangle? Well, the area of the triangle is equal to a half AB sine C, where of course A and B are two sides of the triangle and C is the angle in between them. So if this was side little a, this would be side little b, and this would be angle C in between them if we were working out the area of this triangle here. So that's going to be a half multiplied by 8 multiplied by 8 multiplied by sine of the angle pi by 12. Now, this is where you need to input the part in red straight into your calculator without trying to convert pi by 12 into degrees and then taking the sine of it. So what I want you to do is input this whole calculation, 8 pi by 3, take away a half times 8 times 8 times sine pi by 12 into your calculator in one line, and then see whether you get the same answer as I do. Now, you should find you get a very small decimal answer of 0.09537 ... So we could say 0.095 centimetres squared to two significant figures. But the key purpose of this calculation here is to make sure that you understand how to perform a calculation like sine pi by 12 using your calculator in radians mode. So it's absolutely crucial that you don't convert the angle to degrees and then just blindly use degree mode. You need to convert the calculator mode to radians mode and then just simply input the calculation, the trigonometrical calculation in radians in your calculator and allow it to do the work. I've seen a lot of people waste a lot of time on questions because they're afraid of using their calculator properly. They try and convert the angle into degrees and then do the calculation, and then at some point, because there's so many calculations involved, they do something silly. It is much, much easier to leave your angle in the measurement it's in, the unit that it's in, so in this case in radians, and change the mode on the calculator. So the mode on the calculator should match the type of angle that you are working with. If you're working in degrees, your calculator should be in degrees mode. If you're working in radians, your calculator should be in radians mode. So we're going to finish off by looking at 4 slightly more complex problems. So let's read it through and let's sketch a clear diagram of what we have here. So we have a sector of a circle which has an angle 1.5 radians. Note that as soon as you see the word radians, put your calculator in radians mode so you don't get the wrong answers if you've got to do any trigonometrical work. And an area of 27 centimetres squared, and you have got to find the perimeter of the sector. So we need to start off by sketching the sector of our circle. So we know that the angle here is 1.5 radians. So you can see the question uses the word radian here just to be really clear which unit we're working in. And we don't know what the radius of this is. All we know is that the area is 27 centimetres squared. So we know that the area of the sector can be calculated using the formula a half r squared multiplied by theta. So I know that a half r squared multiplied by 1.5, which is the angle, is equal to 27. So rearrange this and work out what the radius is. And conveniently, the radius works out to be an integer value of 6 centimetres. Now, the perimeter is going to be equal to 2 lots of the radius, here and here, add the arc length. So we want 2 lots of the radius plus our arc length. So 2 lots of the radius is simply 12, and our arc length is given by r theta in radians again. So that's 12 plus 6, which is the radius, multiplied by the angle theta in radians, which is 1.5, and this then gives us a very neat overall value for the perimeter, which is 21 centimetres. Let's look at problem 2. We've been given a nice diagram for this. So the diagram shows the sector OAB with a sector angle 1.2 radians, again, so 1.2 radians, and an arc length of 4.2 centimetres. It also shows the chord AB. So, part 1, find the radius of this sector. So, what do we know? We've been given the arc length, which is 4.2, and we know arc length is equal to r theta. So 4.2 is equal to r, the radius, multiplied by theta, the angle, which is 1.2 radians. So from here, we can very easily work out that the radius is equal to 3.5 centimetres. And I'm just going to add that to my diagram for clarity. Now, what about part 2? Make sure you understand the question and read it carefully. Calculate the perpendicular distance of the chord AB from O. Now, the perpendicular distance will, of course, bisect this angle 1.2, and it's this. So if I call that M for the midpoint of AB, that means we need to find the distance OM. Now, there are lots of different ways in which we can actually go about this. I'm going to sketch out the triangle, the right-angled triangle that has M here, O here, and B here. And remember, we're finding the distance OM. I know that OB is the radius that I calculated in part 1, so 3.5 centimetres. And my angle is, of course, this angle here, which is half the overall angle of the sector. So this angle here is 0.6 radians. So what am I going to do? I'm going to try and find OM, which is the adjacent, and I have the hypotenuse, so I know that cos of 0.6 is equal to OM divided by the hypotenuse 3.5, so adjacent over hypotenuse, and I can simply use some very, very basic trigonometry, 3.5 multiplied by the cosine of 0.6. Now, your calculator must be in radians, okay? So again, as I keep emphasising, don't bother trying to convert the angle to degrees and then use your calculator in degrees mode. The question is in radians, your calculator should be in radians mode. So I want you to just input this into your calculator straight away, and you see that you get 2.8886 ... So 2.89 centimetres to 3 significant figures if you've done the calculation correctly. So let's have a look at problem number 3. It's a little bit more complex than the other questions that we've done, so let's read it through carefully. So Charles has a slice of cake. Its cross-section is a sector of a circle as shown, and the radius is r centimetres. So here's the radius of the full sector, which I'm going to call OAB for clarity. So the radius is r and the sector angle is pi by 6. He wants to give half of the slice to Jan. He makes a cut across the sector as shown. Now, we've then got to answer this part of the question, which says show that when they each have half the slice, this is true. Now that's why this is a more complex question, because we've been given some information and we've then got to apply that information somehow and then get to an answer. But there's no directive here. There's no part 1, work out arc length, part 2, work out area. It's a much more complex question than the very basic ones we've done so far. There will always be a hook in these questions. There will always be one vital piece of information that tells you how to start your work. And it's this. He wants to give half the slice to Jan. So we know that when that line is drawn, that dotted line is drawn across the sector, this portion here, this triangle, is half the area of the whole sector. So let's put on some markings. So P and Q will label these points. And what I'm going to start off by doing is working out the area of the sector OAB, first of all. Now that is equal to a half r squared theta, because we're working in radians. That was very clear in the question. The angles in terms of pi, and they've specifically said radians. So that's a half r squared multiplied by pi by 6, which simplifies to give us pi r squared over 12. Now, let's work out the area of the triangle. So the area of my triangle, OPQ, remember we used the formula previously, a half AB sine C, where A and B are 2 adjacent sides and C is the angle in between them. So that's a half multiplied by A multiplied by A. So I'm using a side and a side. And then we want to multiply by sine of the angle in between them. So that's sine pi by 6. Okay. So that's a half multiplied by a squared multiplied by, now sine pi by 6 we know is a half, but you can also input that into your calculator if you want to work it out, as long as it's in radians mode, so we get a half. So we have a squared over 4. And that's the area of the triangle. Now, going back to the original information, we know that the area of the triangle is equal to a half of the area of the sector, because the dotted line splits the two into two equally sized portions. So I know that a squared over 4, which is the area of the triangle, must be equal to a half of the area of the sector, which is pi r squared by 12. Pi r squared over 12. Now, look at where you're aiming for. We need to show that this is true, so we need to rearrange this result for a and then simplify it. So what can we do? We can say that a squared is equal to 4 pi r squared over 24, which simplifies down to give me pi r squared over 6. So if we then square root both sides of this, you can see that a is equal to r and then the square root of pi by 6, which is what was required. So the last question is really interesting because it has a mixture of degrees and radians involved, so we need to be very careful with our calculator work. So the diagram shows a village green which is bordered by 3 straight roads. The road AC runs north and the measurements are shown in metres. So part 1, calculate the bearing of B from C, giving your answer to the nearest 0.1 degrees. So look at that. The calculation is in degrees. Make sure your calculator is in degrees mode to start off with. So the bearing of B from C, that means we start from the north line here at C and we've got to work out this angle here, and that's the bearing. Now, the easiest way for us to do that would be to work out this angle here, theta, and then subtract it from 180 degrees. So that's what I'm going to do. First of all, for part 1, I'm going to find theta, first of all. And to do that, I'm going to need to use the cosine rule, which tells me, of course, that a squared is equal to b squared plus c squared minus 2bc cos a. So that tells me that 189 squared is 118 squared plus 82 squared minus 2 times 118 multiplied by 82 multiplied by cos of theta. Okay, so we need to rearrange this and make sure you do this yourself. Don't just copy this down. Try this yourself. Check you get the same answers. So I'm going to work out what cos theta is. And remember, after that, we're then going to work out theta using inverse cosine on our calculator. And we must be in degrees for this to work correctly. So change out of radians mode and into degrees mode. So you should find that cos theta, if you've done it correctly, is negative 0.7788 ... And then this is a real check here. Using the inverse cosine button on your calculator in degrees, you should get 141.1586 ... And I'm not going to round that yet because we're being asked to work out the bearing. So I need to subtract this value of theta from 180 degrees to get the correct answer. So that works out to be 38.841. So to the nearest 0.1 of a degree, that's 38.8 degrees. Now, it's a bearing, so it should be in 3 figures, so 038.8 degrees is our answer as a final value. Now, part 2 of the question is actually really easy because we've done all the hard work in part 1. We've got to calculate the area of the village green. So it's a triangle. Area of a triangle is a half AB sine C. So it's a half multiplied by 118 multiplied by 82 multiplied by sine of theta, which is 141.15. And if you haven't already done that, it would have been very sensible to save this in a calculator memory, so you've got that value there to use. Don't forget your calculator has got to be in degrees, otherwise this is simply not going to work. You're not going to get the correct answer. Try it yourself, see if you get the same answer as me, and you should find, if you've done it correctly, you get an answer of 3034.227, etc. So I think we'll round that to 3034 metres squared to the nearest whole number. Now, read part 3 of the question really carefully, because the question now moves into having to use radians here. So the road AB is replaced by a new road, as you can see in the diagram, and the village green, which was the triangle ABC, is extended to the new road, and you can see the segment, the darker shaded part that's been added on. So the new road is the arc of a circle with a centre at O. So here's the new road, and a radius of 130 metres. So you can see the radius there as well. Show that angle AOB is 1.63 radians. So where's angle AOB? It's this angle here. And we've got to show it's 1.63 radians. Now, how can we do that? Well, we know that this length here is 189 degrees. So if I sketch out the triangle with a little bit more detail to it, let's do that down here. So part 3, part A, I'm going to sketch out O to B, and then I'm going to add in a point here, which is the middle of AB, and I'm going to draw in a right angled triangle like that. So here is M, we get a right angled triangle, and this is half of the angle that I actually want to calculate here. So what do we know? Well, we know that this side OB is 130 metres, that's the radius, and we know B to M is a half of 189, so it's 94.5. So if I call this angle here alpha, I'm not going to use theta, we used it in the previous question, then we can see that sine of alpha is equal to the opposite 94.5 divided by the hypotenuse of 130, and alpha can then be worked out using the inverse sine. You must be in radians, however. Remember, the question here is in radians, and if you don't convert your calculator in radians, you're going to get the wrong answer at the end. So alpha works out to be 0.8138 ... but that's not angle AOB, it's only half of the angle there, so we can then work out that angle AOB is double alpha. So multiply that by 2, and you will get the answer that you want. So 1.6276, so 1.63 radians, or you can use the little c for circular measure, correct to 3SF. Now, the last part, B. Show that the area of land added to the village green, so that's the area of this segment here, is 5,300 metres squared, correct to 2 significant figures. So we've been here before. The area of the segment is equal to the area of the sector, OAB, take away the area of the triangle, OAB. So let's work this out. The area of the sector, first of all, is equal to a half multiplied by r squared multiplied by theta, and then the area of this triangle is a half AB sine C, so we can use both of these two formulae together. So what about the sector, first of all? So that's a half multiplied by the radius of 130 squared multiplied by the angle, which we now know is 1.6276 ... Now I recommend, again as always, put this into a calculator memory so you can then use that here in its exact form. And we want to subtract from that a half multiplied by A, which is 130, multiplied by B, which is 130. So just in case you're not sure what we're doing, we're working out the area of this whole triangle here. And we can see that if we call that A and that B, then there's the angle C in between them. So a half times A times B times sine of 1.6276. This is where it's really helpful to have all of this angle stored in your calculator, and we're just going to input that directly into our calculator, one single long calculation, and we'll know if you've done it correctly because the answer was given in the question. And you should find you get as an exact answer, and it's important to write the exact answer down first of all, 5,317.396, which of course rounds to 5,300 metres squared, correct to significant figures. And we're done.